Welcome, Roxy and Sophia and Maddie and Jose and Jack and Marina and Marquette and Luz. Thanks for coming. We have lots to do today, important stuff. So let's get to the quiz and let's take a look at it. Okay, so here is the quiz. And what it says is, suppose that physical therapy session time is normally distributed with mean 45 minutes and standard deviation 8 minutes. Okay. Again, the word suppose means I somewhat made it up, just let you know. I did look online and it did say the average time was about 45 minutes and they gave a spread and 8 sounded about right for the spread. So the normal was just a total guess. That's a big assumption. But we're going to find out, and this is very important, we're going to find out today that for things you do in statistics, not just computing probabilities, but for statistics, you won't need to assume a normal distribution even when you don't start with one. But that's a little later today. So the first question is, write down in symbols the distribution for physical therapy session time. Okay, let me copy and paste it so we can see it a little better. So you just skip the calculator. Okay, what does it look like in symbols when I say write down the distribution? What do I mean by that? Who remembers? We did it 2 days ago. Hopefully you can all hear me. I don't see you all jumping in. Do you remember what it means? Yeah, but the first thing is you got to get the variable. What's the variable when we're looking at things like physical therapy time? What letter do we use? Yeah, that's X. So you go X, and then you have to do tilde. So that means X has the distribution, that is, and then N for normal, and then 45, 8, because the mean is 45 and the standard deviation is 8. Any questions on that? Again, not a trick question. I try to make these very similar to the examples that I give in class, the time before. So we saw an X tilde N with the mean and standard deviation. It wasn't physical therapy. It wasn't 45 and 8, but it was the same idea. Any questions on the first part? Okay, so the second part is, if a randomly selected physical therapy session is observed, what is the probability that will last at least 50 minutes? Okay, so we want the probability that X is greater than 50. Okay, by the way, I don't know if I mentioned it last time, technically at least is greater than or equal to, but when we're working with a normal distribution and any continuous distribution, greater than and greater than or equal to are exactly the same, because the probability of being exactly a value is always 0. So it makes it easier to type. Any questions on that? All right, what do I do next? Z-score. We don't need to get a Z-score. Definitely don't.
Use the normal probability calculator.
Yeah, that's the next thing we got to do is we got to go to the normal probability calculator. And again, we have written out, we have normal distribution 45, 8. We want greater than 50. So then we just go to the calculator and we want the normal probability calculator because we have a normal distribution. We know the mean was 45. The standard deviation was 8. We want greater than 50. So what goes in the low? Yeah, the low is 50. And what goes in the high? So if we want greater than 50, what goes in the high? What's the biggest number greater than 50? Yeah, so it's infinity, and you write a bunch of nines. Again, 4 digits is enough because these are 2-digit numbers, add 2 nines, and that'll always work. And then P equals blank. So let me stop. Any questions at all on coming up with this solution? And I hit calculate. Any questions on that? You just pop in a bunch of the decimals. Okay, so if there's no questions, wait, I want that one. So what I can say is that is equal to 0.2659855, or if you want 0.27, that's fine. I just did a copy and paste. Any questions on question 2? Okay, question 3 is, what is the third quartile for physical therapy session time? So if I'm asking for a third quartile, what does that mean?
75th percentile.
Yeah, that's a 75th percentile. So that means we want to find the x so that the probability of being less than x is 0.75. So let me just type that out. Find x such that the probability, right, prob of being less than x is 0.75. So now I go to my calculator. So 0.75, where does that go?
That probability, P.
Mm-hmm. So that's 0.75. And I want to find x such that the probability of being less than x is 0.75. So it's not 50 and 9999. What is it? My mean and standard deviation don't change, but what about the low and the high? What's the low? So what do I do for the low? If I want the probability less than x to be 0.75.
0.
You could do 0, but probably negative a bunch of nines is better. You'll get the same answer in this case. So, and what about the high?
Leave it blank.
Yep, that one we leave blank because that's the whole point. We want to find that value. And I calculate. And there it is. A little more than 50, 50.3959 is good enough. Any questions on that one? So let me write. So then the third quartile is 50.3959. Any questions at all on number 3? Okay, so number 4 is, what are the lower and upper bounds for the middle 80% of physical therapy session times? How do we do that one? That one takes some more work. Anyone have a strategy? If I want the middle 80%. It's kind of what we did a couple days ago. I don't see anyone jumping in. Okay, so let me remind you, if you want the middle, if the middle is 80%. So first thing, when you say middle 80%, that's an area. That means 0.8 is the area in the middle. So let me just write that out. So 0.8 is the area in the middle. Okay. You could draw a normal curve and you can shade in the middle 80%. Well, if 80% is in the middle, how much is outside? If 0.8 is in the middle, how much is outside? Any thoughts? Yeah, 0.2. Because let me actually write out the math. 1 minus 0.8 equals 0.2 is on the outside. How much is in the left side? If 0.2 or 20% is on the left side, on the outside, how much is on the left side? Yeah, 0.1, because you know the normal distribution is symmetric. So if the left and right combined make 0.2, then the left is 0.1. So 0.1 is on the left. Okay. By the way, how much is on the right? And that's an easy answer. So if 0.1 is on the left tail, how much is on the right tail? Yeah, 0.1, again, on the right tail, because of symmetry. Any questions so far? All right, so now let's go get the bounds. We know that 0.1 is on the right, so that means we want the 10th percentile. So let's go and do it. So we do exactly the same as what we just did, except instead of P be 0.75, we let P be 0.1. And we let the high be blank. And I hit calculate. And I get about 34 point. Let's do a bunch of decimals. So that is our lower bound. Let's write that out. Now let's get the upper bound. Okay, if 10% is on the right, then what are the low and high this time? What do we do? If we want the right now instead of the left.
Low is 0.9, or the probability would be 0.9.
Or we could leave it as 0.1. I want to leave it as 0.1. And then the low is what we want.
So the high would be 9, 9, 9, 9.
Yeah, the high would be a bunch of nines. You could do it with a 0.9, and that will work also. But I wanted to kind of explain this way because we're looking at the two tails. And this makes it feel like a tail. And then I hit calculate. And I get 55.2524-ish. So that means the upper bound is 55.2524 around. Maybe I'll make that 0.6 so we get the same number of decimals. Any questions at all on this quiz? Okay, most important thing is practice. By the way, do you think this type of material is going to be on your exam? Next week's exam? Yes, yes. Kind of my philosophy is if you've been if you've had to do your homework assignments, your chapter assignments, then it's fair game to put on the exam. Whereas I don't feel comfortable with chapter 7 because those assignments aren't due until a week from Sunday. So it's not, to me, it's not, I don't think it's fair to make you be tested on something that you haven't done your assignments on yet. So that's why chapter 6 is and chapter 7 isn't on the exam. Any questions at all on 1, 2, 3, or 4? Any questions? Okay, if there's no questions, let's go back to the list of things to do. Whoops, not that one. That one. Wrong class. Okay, so are there any questions about anything else? It says Q&A time. If there are, I'll be happy to answer. Any questions? Okay, if there's no questions, then let's get into the new material. And I'm going to kind of do it by example because I think it helps to see an example and then get into the kind of intense notation and a lot of language. Today is a big language notation day. I should warn you about that, and also very useful. Are there any other exam practice problems other than the PDF? So first thing, I don't think I made a PDF. I have a Google Doc. I got a Canvas set. We got a HTML doc. I tend not to do PDF, so I'm not sure what you're talking about. It's probably not a PDF. Probably felt like one, but maybe not. But if you're looking for practice, and we'll talk about it Tuesday too, but if you're looking to practice now, then here's the best practices. Well, one is redo all the quizzes, okay? And what I recommend is go back to the webinar and kind of look at the quiz question, see if you can do it before I do it, okay? Does that make sense? So that's definitely a good practice because I think the quizzes are the best idea of what test problems will look like because your quiz is on Canvas. Does that make sense? So that's number one. Number two, and I don't know, I think I put it in there, but it's a little scary. And I'll be talking about it. Let's do this. I'll be talking about it Tuesday also, because we're going to do that. And that is, I think it's in modules. Oh, I gotta move my Zoom stuff so I can get to a click. There we go. It's been a little while since I looked at it. DocX. Okay, yeah, do DocX. Yeah, I'm not a very big PDF lover, so that's why I was surprised when he said PDF. Yeah, so there's a DocX. So there's a lot of different things. And so if you go to not week 8, I want to go to week 5, I believe. Is it 5? Oh yeah, I didn't put them in here. That's why. Yeah, it was 5. Yeah, I will show you on Tuesday, but I can get to it now if you want. I need to go to my Google. I was going to do this on Tuesday, but I can show you now. And this is going to be a little scary because I think it's like 200 pages long. But if you want X problems, there's a lot of them. And that's for the whole course, not just for, our part. Takes a bit because it's so long, it needs to load up. Still loading. It'll get there. But this is a list of questions that I've did. They're pre-COVID questions. So they're more in-class kind of questions because this is like 15 years of giving tests. But I'll put in the chat, but it takes a moment to happen because it's such a big document. All right, so there's a list of a lot of questions. So there's some more. There's a lot of practice problems. And of course, you can always go back and do your homework assignment in review mode. Okay, the chapter assignments. So those are more problems you can do. So there's definitely a lot, unlimited amount, basically. Hopefully that answers your question. Sorry, it took a bit because loading this is takes so long because it's so big. Any other questions? Any other questions? Okay, then I have a question for you, and I'm going to let you choose. Okay, maybe someone has an idea. Is there anything you are interested in about each other, quantitative, that we can find out? Some quantitative survey question. Anything that you're curious about that we're going to ask each other? And by the way, the chat box is not part of the recording. So you don't have to feel uncomfortable about that. No one will know who said what because I won't give names. Okay, if I'm not seeing, I'll give you a couple seconds. Otherwise, I'll make something up, but I always like to hear what you're interested in. Ah, that's a good one. How many face masks do you own? Okay, so here's a question for you. So what I want you to do is I want you to put in your chat box the answer to that question. And by the way, it's recorded, but I'm not going to, what's in the chat box is not. So I'm going to put a bunch of numbers. No one will know. Disposable, countable, reusable. So Roxy, that's your choice. What are you interested in? Okay, so only reusable then. Okay, and I'll do mine too. Why not? So I have, let me count. 1, 2, I have 3. Spelling doesn't matter. Doesn't show on the webinar. So let's see what we got. We got 4, 2, 3, 10, 6. And 12. And I'm not sure if that's everyone, but Again, it's not important. It's not like if you get it wrong, I'm going to lose points or something. Just put in a number. That's all I care about. And again, I'm not saying who it is, so there's nothing you have to worry about the recording and all that. It's just a number. Anyone else? Okay, if not, then we'll look at this. And what I'm going to do, here's the next question. Okay, so first thing is we're going to call this the population. So consider this as the population. Okay, so this is a population. I know it's only a population for size 7, but that's okay. So now the next question I have for you. Okay, and notice, by the way, I'm going to order them. So 4 is 1, 3 is number 2, 2 is number 3. Hopefully you understand. So we're just going to order them, put them in order. Okay, the next thing I want you to do is pick, how about 3 random numbers between 1 and 7. Okay, and I don't know if you remember, how did I tell you really the only successful way you can truly pick random numbers are? Yeah, computer, or even faster probably for you guys, maybe I'm wrong, is a smartphone. So here's what I want you to do. I want you to pick up your smartphone and I want you to ask, give me 3 random numbers between 1 and 7. Okay.
3 random numbers between 1 and 7.
Yep. Exactly. Ask your smartphone. Don't list the numbers yet. Just write them down on a piece of paper. Because the numbers you have are not important. The other way to do it, by the way, I can even pop this in and go back to the calculator menu. I don't think I've used this one too much, but I can do random number generator. So I'm going to pick my 3. You can't use mine. I mean, you can do your own. So we have the low is 1, the high is 7. I'm going to get a number 4, get another one 5, get another one 2. So 2, 4, and 5. So mine are 2, 4, and 5. So I'm going to show you my example, but I want you to do an example too. So you could use my random number generator too if you want. Okay, so it was 2, 4, 5. So note that what I picked was 2, 4, 5. Oops, keep going to the wrong one. There we go. So I picked 2, 4, 5. And in particular, 2, 4, 5, the second number was a 3. The fourth number was a 3. And the fifth number was a 10. So this is my sample. Any questions on what I just did? Any questions on that? Because I got the second number, the fourth number, and the fifth number, and that was 3, 3, and 10. Okay, the next thing I want to do is I'm going to find my sample mean. And my sample mean, you could use a calculator. I could do this easily in my head. 3 plus 3 plus 10 over 3 is 16 thirds. Okay, and 16 thirds is about 5.3. Any questions on that? Okay, what I want you to do.
Wait, should we be doing this with the numbers we have?
Yeah, do it with the numbers you have, not my numbers. It's very important we have different numbers here. Okay, because the chance, I mean, you probably didn't pick the second, fourth, and fifth numbers. You probably picked different ones from this list. So I want you to put in the chat box what your sample means are. Okay, 3.3. Let's hear some more. 4.67. I'm going to call it 4.7. Let's do one decimal place is good enough. Just for today. Okay, and again, if you don't understand it, ask me, I'll help you. But it is important to understand what's going on here.
Wait, so are we like finding the sample mean for our 3 random numbers, or do the
Yep,
random numbers
exactly.
correlate to the sample that we collected?
Okay, so you're going to pick 3 numbers between 1 and 7. You're going to look to see which 3 they correspond from this list. So mine were 3, 3, and 10, because my 3 numbers I picked were 2, 4, and 5. Do you see? Then you're going to take a mean of those 3 numbers. Is that confusing, or do you understand that?
No.
Okay, so let's see some more. 2.7. And 13 is not possible. You can't have an average of 3 of these numbers that's bigger than 12. Right? If you pick numbers 4, 3, 2, 3, 10, 6, and 12, you pick 3 of those and took an average, you can't get 13. So another 3.7. Does that make sense that you can't get 13?
I mean, yeah, but I did.
Did you divide by 3?
Don't know how.
Did you add them and divide by 3? That's how you find a mean, right? You add the 3 numbers. You pick 3 of these numbers, and then you divide it by 3. Added these 3 and divided by 3. You can't get 13. Okay, make sure you put parentheses around the sum if you're doing it in the calculator. So parenthesis, first number plus second number plus third number, and the parenthesis divided by 3. That's a possibility. I'm just seeing things that can go wrong. But you can't get a number. You can't have an average of 3 of these small numbers and get 13. It's just not possible. So one thinking is maybe it was a calculator error for getting a parentheses. I'm not sure. Sorry, I can't read your mind. Okay. All right. So I want to look at all these different things. Okay. First is I can take 4, 3, 2, 3. In fact, I'm going to do that just for fun. Go back to the calculator. And I'm just going to go statistics. And this is going to be the population standard deviation because I said this is our whole population. And then hit calculate. Notice the mean of the numbers is 5.7 about. And the standard deviation, because that's the other number I'm interested in, is 3.6 or so. Any questions on that so far? So the mean is 5.7, and let's write some stuff out. So the mean of the population, what symbol do we use for the mean of the population? Who remembers? Very important, by the way.
Yeah.
Mu. So we're going to write mu was equal to 5.7. There we go, Roxy, 8.6. Okay, that's possible. Let me make sure 28. Yeah, that's possible. Okay, so another sample mean was 8.6. Okay, so mu is 5.7. Let me ask you, this is for me, and you have your own. My sample mean was 5.3. What symbol do I use for 5.3? Do you remember the symbol for the sample mean? Not S. S is for sample standard deviation. So we'll get there too. But what's a symbol for the sample mean? It's hard to type. That's a hint. You really can't type it. You have to kind of spell it out.
Wait, how did you get mu for this one?
I went to the calculator, and that was the mean of all the numbers. Do you see? I put all the numbers in, and I hit calculate, and it gave me the mean. Does that make sense? Nothing too fancy. I just found the mean using the calculator, and that's the mean of all the numbers, all 7 of them. So who remembers the symbol for the sample mean? So if you don't remember, I'll write it in. It's X with a bar on it. Does that ring a bell? It's not X, it's X bar. Okay, and my X bar, you have different X bars. My X bar was 5.3. Let me make this a little bigger because symbols tend to get small. Okay, we also had the population standard deviation. The population standard deviation was again 3.6 about. And what symbol do you use for the population standard deviation? Who remembers? Don't see jumping in. Use a sigma. So that's that Greek letter sigma. And again, that Greek letter sigma was 3.6, 3.6. Okay, I was able to do the mean in my head. I can't do the standard deviation in my head, but that's okay because I can find it, 3,310. So I can go to my calculator, pop in 3,310, hit, now it's a sample standard deviation, and hit calculate. And the standard deviation, 4.0 is a sample standard deviation. All right, what letter to use for a sample standard deviation? Since I said it 5 minutes ago.
S.
S. So S is equal to 4.0. Any questions on these symbols? Okay, now comes the next interesting question. If you look at this, and I'm going to put mine in there too, 5.3. I have a list of numbers, don't I? Okay, if we look at all of our sample means, there's a list of numbers here, isn't there? When you have a list of numbers, you could find the mean and the standard deviation for those lists, for those numbers. Any questions on that idea? Okay, now I'm going to extend it out a bit. We found some of them. There's a lot more. And in fact, if you have 7 numbers and you're picking 3, who remembers how many different ways are there? How do you find how many ways are there of picking 3 out of 7 numbers? Remember how to find that out? Okay, so if you don't, if order doesn't matter, that was that combinations calculator. Do you remember that? And turns out to be very large, by the way. I'm not going to get them all, but we got some of them. Hopefully you understand that. I thought the O thing was standard deviation. I'm not sure what O is. Sigma. Sigma. So you thought the sigma was standard deviation. Okay, so let me explain what these are. Sigma is the standard deviation of the whole population. So the standard deviation of 4, 3, 2, 3, 10, 6, 12, that's the entire population of all of us. That is sigma is 3.6. S is not the standard deviation of these 7 numbers. S is going to be the standard deviation of the sample, which is just these 3 because I only picked 3 numbers from my 7. And that's why it's not the same. So S is the sample standard deviation from the sample I picked from the population. Does that make sense? So there's a standard deviation of the whole population, that's sigma. And then there's a standard deviation of our sample, that's S. Did I lose you there, or does that make sense? Okay, so it turns out standard deviation comes in different places. One for the population, one for the sample. It's actually going to come in another spot too today, in a bit. Okay, good. All right, so we could look at all the sample means, right? So now I want to write out, because this is the new stuff. So far, all I've done is review of what we've already learned. But if we don't review this, I think there's almost no chance of understanding what's coming next. So if we consider the collection of all possible sample means, right? We got some of them, 3.3, 4.7, 2.7, 3.7, 8.6, and 5.3. There's a lot more of them. We don't have enough time to look at them all. Okay, but in theory, you can think about the collection of all possible sample means. This is its own data set with a very large size. Okay, so again, I started with 7 in the population. I'm picking 3. But if you look at the number of ways of picking 3 out of 7, especially if you allow repetition, then it's actually really big. Okay, it's really big. It's 7 cubed. Okay, that's in the hundreds instead of just 3 or 7. Okay, so we get a data set with a very large size where the data values are each of the sample means. Okay, when we have a data set, we can consider its distribution. So when I say consider its distribution, that's things like, what is the mean of that? What is the standard deviation of that? What is the shape if you drew a histogram of the sample, all possible sample means? What's it going to look like? So we get the following. The mean of all possible sample means is noted or notated by, so it's a mean of means. So if all possible, so there's going to be a mu, but it's a mean of sample means. So it's going to be sub x bar. So mu sub x bar is a mean of all possible sample means. Okay, when you have a data set, the mean is one of the things you're interested in. What's the other biggie? What's the other big statistic you're interested in when you have a data set? Think about your project. What's the other biggie besides the mean? Yeah, the standard deviation. So the standard deviation of all possible sample means is denoted by, well, it's a standard deviation. So now we're going to write sigma for standard deviation, but it's the standard deviation of sample means. So it's sigma sub x bar. And is also called the standard error. Okay, and you've seen the standard error on the spreadsheet. I know a couple of people asked about it, emailed, I think. I don't remember, maybe in the webinar, but I remember hearing a question about standard error. I'm like, we're not there yet, but we will be. Okay, might have been office hours. Any questions about this? Because whenever you have a data set, there's going to be a mean and a standard deviation. Any questions? Okay, now we're going to explore. So there's a mean, there's a standard deviation, and then there's a shape of the distribution. The shape of the distribution, I'm going to do some exploring. So I actually programmed an exploration, a discover the central limit theorem activity.
Wait, can you go back for a second? Sorry, I need to write the thing.
Okay. Tell me when you're ready, because we definitely need to do some exploring.
Okay.
Okay, so let's go back. Let's go to explore. And I'm just going to start. Let's suppose we started with a uniform distribution. Okay. So the computer just created a uniform distribution. The mean is 200 and the standard deviation is around 115 or so. Okay. So now let's suppose that we take samples. And let's suppose we take samples of, say, size 100. And what we're going to do is we're going to pick a sample size 100. We're going to pick another sample size 100. We're going to pick thousands of samples of size 100. Now, we can't do that without giving up because it'll take way too long. But computers are really good at this. And I was able to code the computer to do it because I'm too lazy. I won't do it myself, but I can code it. And it will calculate the mean, the standard deviation of the sampling distribution, which means of all the different sample means that you can get by grabbing things from a uniform distribution. If I do that and draw a histogram, do you think it's going to look uniform? What do you think? What's your guess? Any guess? I'm just looking for a guess. I don't expect you to get it right. Do you think it'll look uniform? So we're gonna take 100 randomly selected numbers on this uniform distribution, find the average, take another 100, find an average, keep doing it, and then draw a histogram of all those averages. Do you think it'll look like a uniform distribution? Yes or no? Just a guess. What do you think? Somebody can guess. Remember, if you don't guess, that means you're saying that you just don't understand the thing I say and I need to start reteaching it. Okay? Like teach you how to guess, how to use Zoom. So if you want me to teach you how to use Zoom, I can show you. But everyone's supposed to guess.
Or maybe it means that we just don't understand the concept and that's kind of,
I'm just looking for a yes or no. So the idea is we're gonna pick we're going to pick 100 different numbers in this range here between, say 0 and 400. And then we're going to take the average of those 100. Then we're going to do it again and again and again and again and again and again and again. And we're going to look at a histogram of those averages. I'm looking for yes or no. So if you don't, so what I'm going to do is I'm going to watch your names. And if you don't give me something, maybe I'll take off points off the exam since you're not giving me anything. Would you rather have that? There we go. Now I'm seeing some. Okay. So I see a no. Anyone else? Want to lose points? Okay. See a yes. All right. There's a no. Okay. Oh, we're mixed 50-50. Okay. So let's take a look. There's only one way to find out, and that's to do it. So let's do it. I'm going to hit n equals 100. Takes a minute because, again, it's picking 100. It did 2,500 sets of 100 values in here. Found a mean and standard deviation. Does that look uniform? What do you think? You're allowed to change your answer now. Did we get a uniform distribution or did we get something a little different? Yeah, we got something very different. Okay, and in fact, notice this is unimodal. It's symmetric. Do you see that? This is not that far from being normal. Do you see that? Okay. Notice that the mean of all those collections is basically the same as the original mean. We started with 200, and guess what? The mean of all the X bars is still around 200. Is that clear? How about the standard deviation? If you take the standard deviation of all of those possible sample means, do we get the same standard deviation we started with? Yeah, it's different. Not only is it different, but if you look at it, it's about 1/10 the size, right? If I multiply this number by 10, I get pretty close to 115. So we've got reduced by a factor of around 10. Okay, and I want to note something, and something I would never expect you to guess, but what is the square root of 100? That you should all be able to do without a problem. What's the square root of 100? It's 10. So notice if we start with this sigma and we divide by the square root of 100, we get our sigma sub x bar, something very close to it. Okay, I could do the same thing with n equals 9. Let me click that. Okay, and look at that, it's still not uniform. Okay, it's got some little lumps and stuff, but it's not that different from normal, but it is what it is. Notice that the square root of 9 is 3. If you take 115 and divide by 3, you get around 38. Okay, the mean didn't change. 200, still 200 to even one decimal place.
Wait, just to clarify, so the one on the left is the mean and standard deviation of the entire data set, and the one on the right is the mean of all of the means of a data set and the standard deviation of all standard deviations of a data set?
Yeah, exactly. It's the standard deviations of all those means. So sigma sub x bar means the standard deviation of all the 20,000 sample means that it took. Does that make sense? Every time you take a sample mean.
So how can it have so many sample means?
It could take samples all day long. So the computer took a sample of 9, found the sample mean of that. Then it took another sample of 9, and guess what? It done the sample mean.
So
then it took another sample of 9, and it did it 20,000 times. Computers are very fast, so they can do that. We can't.
That's not really what I'm asking. So is it like taking 9 random values from that data set and finding the mean of that?
Yep. So it's in particular, it's 9 random values in between 0 and 400. There's uniform with average 200, which means it goes from 0 to 400. Do you see that? So it grabs 9 random
Not
numbers from 0 to
really.
400. So mu is 200. That means 200 is right in the center. Do you see that?
How
If
do you know
200
it's
in
four?
this,
How?
huh?
Where is it 400?
Okay, so the center is 200, right? For a uniform distribution, the mean and the median are the same. The mean is always right in the center. And if the center is 200, then the right must be 400. Because you have to walk over 200 to get to the center, and you have to walk 200 more to get to the right, and that's a total 400 of walking. So it picked 9 numbers between 0 and 400, found the mean of those 9 numbers, and then did it again and again and again and again, came up with a new data set, and then found the mean of the data set. It is pretty complicated, but it's very important. Any questions on that? Okay. You can do the same thing with 2, by the way. It's not quite as normal, this one. It's kind of spiky. But I want to show you a new distribution. If we started skewed left and did the same thing with n equals 100, it's not skewed left, is it? Looks pretty normal, doesn't it? But if we did n equals 2, it's still skewed left. So that was not a big enough sample size to get normal. Any questions on this?
So is the goal sampling to get a normal distribution?
That's one of the big goals. There's 2 big goals. One is to get a normal distribution, and the other is to get a small standard error. And I'm going to explain that in a bit. And remember that you divide by the square root of the sample size to get the standard error. So if you use n equals 100, you get to divide by 10, and that really decreases it. If you n equals 2, you don't divide by much of anything, 1.4-ish. Okay, so now that we've got this idea, let's state the big theorem of the whole class. Okay, actually, let me give you the definitions, which I said, but here they are again. The sampling distribution for a statistic for samples of size n is the distribution of all possible sample statistics from samples of size n. So the statistic we looked at was mean. What's the other statistic for another kind of study that might happen besides a mean? For a different type of study? Anyone know? So if you do a yes/no question instead of a quantitative question, what's the big statistic for a yes/no question? Anyone know? For the yes/no question, what's the big statistic? What are you calculating when you do a yes/no survey question? You're not calculating a mean. You're not taking an average of yeses and nos. That doesn't make any sense. But what do you take? Do you remember? We've done it. I don't see y'all jumping in. For the yes/no question, it's the proportion of yeses. So 0.7 or 70% of the people said yes. And that's what you're usually interested in. It's not a mean. Okay, and now comes a nice important definition. It's not that hard, that's the good news. Is a statistic is an unbiased estimator for a parameter if the mean of the sampling distribution for that statistic is equal to that parameter. Okay, so it's kind of fancy wording, so let me explain it. So for example, when we did the the survey question, how many face masks do you own? Then we got a sample. Okay, we grabbed 3 of them, we got a sample. That sample mean is our best guess for the population mean. Do you agree? As long as you have an unbiased sample, that's our best guess. So let me write this down. The sample mean is an unbiased estimator for the population mean. Which means that if you're going to take a sample and you want the best guess at the population mean, use the sample mean. Any questions on that? Okay, let me give you a different question, different survey question idea. Let's suppose instead of asking how many face masks, how many masks do you have, how about how tall are you? Sounds good? And let's suppose our population wasn't just us. Let's suppose it was all of America. Got it? So you surveyed, let's say you surveyed 10 people. And you looked at your data from those 10 people. And what you really wanted to find out was the range, which is the maximum minus the minimum for the population. Do you think your best guess for the population range would be the sample range? So if you randomly grabbed 10 people from the population and looked at the tallest minus the shortest height, do you think that's your best guess for the range, the tallest minus the shortest of the whole population of all of America? Okay, the answer is absolutely not, because the tallest minus the shortest of all of America is probably like 7'6" or something. Okay, maybe 7'2", because you're going to get the super tall person, the 7'9" person, and then subtract that little infant that was just born prematurely and tiny, tiny, tiny. And that range is going to be like 7 foot, over 7 feet. But if you randomly grab 10 people, the chance of you getting anything close to over 7 foot in your range is so tiny. The sample range would be a terrible estimate for the population range. Is that clear? So the sample range is a biased estimator for the population range. Okay. The sample proportion. Do you think that's unbiased or biased? So if you take a sample and you have an unbiased, you did a unbiased survey, randomly select people, and you looked at their average height. Do you think that is your best guess of the average height for Americans? If you could truly randomly select, say, 10 people, would that be your best guess for the average height? So that would be a yes. Okay, what about the yes, no question? Okay, what if you wanted to ask, I don't know, something like, do you live in California? And you wanted the proportion of Americans that lived in California. So you randomly grab 30 Americans and ask, do you live in California? Do you think that'd be a good guess, at least your best guess for the proportion of Americans that live in California? Okay, and the answer is yes. So the sample proportion is an unbiased estimator for the population proportion. Any questions on this? Okay, now that we have that, I'm going to state the central limit theorem, and then we'll take a break after that. But it is the big theorem of the entire class, not the day, the whole course. And here's what it says. It says what we've already seen, basically. It says the sampling distribution for the sample means from samples of size n has mu sub x bar equals mu. We kind of saw that if we looked at the mean of all the samples, that was the same as the mean of the population. On the other hand, the standard deviation of all the samples was not the same as the standard deviation of the population. Sigma sub x bar was sigma divided by the square root of the sample size. Any questions on that? So that's number one. Number two for the central limit theorem is if the population's distribution is normal, or if the sample size is large, greater than 30. Where have you seen greater than 30 in this class before? Where have you seen that? It came up not too long ago. Where have you seen greater than 30? Here's a hint. It was a big deal 2 days ago. Some of you are very stressed, possibly. So where have you seen greater than 30? Someone must remember. I don't want to spend all day waiting. Here's a hint. It was a big part of your grade.
Project?
Your project. Do you remember greater than 30?
Yes.
That was your sample size. Okay, that was because if you don't have greater than 30 for quantitative data, you pretty much have a useless study. Okay, and the big reason is right here, is that if the sample size is large, and for our class we're going to use greater than 30, then the sampling distribution for the mean is also, I'm going to write approximately normal, is also approximately normal. So greater than 30 gives you about a decimal place of accuracy. Greater than 100 gives you a couple decimal places. Most people are okay with one or one sig fig. Okay, this is the central limit theorem. It is the biggest theorem of the entire course. And I'm seeing 5:03 on my clock. Let's take a 5-minute break because you probably need it. And then we'll use this in a deep way. I'll show you how to make money. So I'm going to stop the share, take a little break. And again, we'll come back at 5:08. Okay, let's come back from a bit of a break. Hopefully you're all refreshed. And now it's time to start talking about finances. I like to use this stuff, and this is one of my favorite examples because it really talks about what we're doing. And I'm going to share the screen. I got some questions for you. Okay, so let's suppose you put $1,000 into the bank. Okay, whatever your favorite bank is, it could be Bank of America, Wells Fargo, Eldorado Savings, whatever. You put $1,000 into a major bank. What's the probability you're going to end up losing money after 1 year? This is an easy question. That's the hint. Yeah, it's basically zero. Okay, because bank money you put in the bank is what's called FDIC insured. You pretty much have to not have America after a year. So again, there'll be a lot worse things than losing your some of your $1,000. Okay, so notice, what does the mean? Interest. So what is the interest rate? What do you think the interest rate is if you put $1,000 into the bank? Not zero. If you put it in a savings account, it's not going to be zero. It's not going to be much higher than zero, but it won't be zero. Anyone know any guess on what the interest rate is for bank? 0.001. I'll let that one be. So let's write that down. That's mu equals 0.001. What's sigma? What's the standard deviation? The hint is it's very easy. Any thoughts? Really easy. Don't see y'all jumping in. It's zero. If you know exactly what you're getting, then there is no deviation. In fact, instead of 1,000, let's make it more fun. Let's say you pick $10,000 into the bank. Okay. So because of this, if the standard deviation is zero, then the probability of losing money is zero. Let me write P of lose is equal to zero. So that's easy. Do you agree? All right, now let's get a lot more difficult, or a little more difficult. Okay, suppose that you put the money, your $10,000, into a randomly selected stock. Okay, so you might end up buying Tesla, or you might end up buying Disney. Okay, and when I say buy it, that means you buy that stock. Okay, so the first thing is that, do you think that the mean is 0.001 for stock market? Do you think that's the average return on stock? No, definitely not. Okay, so the first thing is the mean. And I'm going to just write this out. Mu. Depends on how many years you look, but I'm going to go 0.09 in terms of the percent. So 9%. Do you think the standard deviation is zero?
No.
Definitely not. Definitely not. Not all stocks behave the same. They definitely change a lot. Okay, and I don't know the exact standard deviation. I probably should research it someday, but let's suppose that the standard deviation is equal to 0.20, so 20%. Okay, because there's a lot of fluctuation with stocks. Okay, assume that the stock returns are normally distributed. So now what is the probability that you will end up losing money? Okay, so let's suppose, for example, you have $10,000 for next year's education, and you need that $10,000 or you're gonna not be able to go to college. Got it? Okay, so you care a lot. You do not want to lose money. So we want that to be really low. Well, how do we get this probability? And the hint is, this is something you should already know how to do. You don't have to know anything from what we did in the central limit theorem stuff. How do we find that probability? What does it mean to lose money? Down, but in particular, right, it has to do with X. If you lost money, then what do you know about your returns?
Less than 0.
Less than 0. Yeah, it's not, X is not the amount of money that's in the bank. X is the percent that you made. And losing money means you had a negative return. So less than 0. Okay, notice also that we have X tilde N, normally distributed because we assumed it's normally distributed. And then 0.09 for the mean and 0.20 for the standard deviation. It's very important to know how to write down the distribution. Any questions at all on this piece so far? Okay, do you know how to find this probability? What do I have to do? So how do you find this probability? And the hint is, think about the quiz you took today. That's a hint. Do you know how to find this probability?
Use the normal probability calculator.
Exactly. We're going to use a normal probability calculator. Okay. So let's do that. Again, there's no way you're going to do this without the calculator. That's not going to happen. So let's go to the normal probability calculator. Okay. And what's the low? If we want the probability that X is less than 0, what's the low?
Negative.
Yeah, negative. Don't even need that many 9s because these numbers are all tiny anyway. What's the high? So what's the high? Easy. That's a hint. 0. We want the probability is less than 0. That means it's between negative infinity and 0. The mean we said was 0.09, and the standard deviation was 0.2. And I hit calculate. Okay, and we're looking at about a 33% chance. Any questions on that? So let's go back. So there is about 33% chance of losing money. All right, so let me ask you something. If this is for your education, and again, if you lose money, that means you drop out of college. Do you think you should put your $10,000 into a stock?
No.
Bad idea. Okay, don't do it. Got it? Because you might lose a lot of money and then you're screwed. You're going to drop out of college and it's awful. All right, now I'm going to go into something a little deeper, a lot deeper actually. And that is, I'm going to share another thing. Have you seen this kind of chart?
Yes.
Okay. Have you heard of Dow? Do you know what Dow is? Do you know what it stands for?
The Dow Jones Industrial Average or something.
Exactly. It's called the Dow Jones Industrial Average. Okay. And as Jack said, there are 30 companies. Okay. So there are 30 companies in the Dow Jones Industrial Average. All right. Now let's go back and I'm going to write a new question. Suppose you put your $10,000 into a Dow Jones index fund. Okay. And by the way, these things exist. It's called an index fund. And what that means is you put that money up and it gets basically evenly distributed amongst the 30 companies. Any questions on that?
Isn't the financial bar to entry on that pretty high though?
10,000 is never a problem. $10, that's probably not enough. Yeah, no, if you had 10,000, you could definitely put it into the Dow Jones Index Fund. Yeah, it's not that high. Okay. Okay, so you can trust me on that one. Do you know why you can definitely trust me? Not because I'm a mathematician, by the way. Any guesses? Okay, I'll tell you when I'm done with this, and then you'll understand. Okay, so now what is the probability of losing money? Oh, the question is, why do I know about it? Why do you not need $1 million? Why can you do it with just 10,000 or something or a little more? Okay, and that's a big question. So what is the probability of losing money? And we're going to assume that the Dow Jones is a representative sample. And that the stocks are independent of each other. Which they're not quite. So I'm letting you know there's an assumption which is not quite right. It turns out that if you do it long term, then it's a decent assumption. But for 1 year, it's probably not a good assumption. But if you do it over, say, a 10-year time, or let me just put it this way, an 18-year time, okay, actually a little more than 17 years, then this assumption is fine. All right. Well, what's happening now? How is this different than investing in one stock? How is this a different question, a very different question than the last one where there was a 33% chance of losing money? Yeah, it's more than one company. What we're doing is we are basically randomly selecting 30 companies, taking an average of those 30 companies, and that is our new investment. This is the central limit theorem. Okay, because that's exactly what the central limit theorem is about. It means that you're not doing one individual, you're taking a group with a sample size of 30 in this case, and you're looking at the average of that, and you're finding out what is the distribution of averages. And you want to find out now, based on that new distribution, what is the probability of losing money? Any questions on that? All right, so what we can do now is we can use the central limit theorem. And we can say that we no longer are going to have X because we're not taking an individual stock. What symbol do we use for the average of our 30 stocks that we've selected? I asked this before and no one got the symbol either, but maybe you get it now because it hasn't changed.
X bar.
Yeah, X bar. It's not X, it's X bar because it's the average of 30 stocks that we're looking at. We're not looking at a single stock anymore. So now it's going to be X bar. So I'll put a bar on it. And then I can go tilde. Oops. And that says N. And by the way, even without the assumption, 30 isn't really over 30, but it's close enough that you're probably pretty good. Okay, it's not perfect though. Okay, but if we assume it's the original is normal, there's no problem. And then we know that the mean of the sampling distribution is the same as the mean of the population, which was 0.9, comma. Okay, and then the mean, the standard deviation of the sampling distribution is not the same thing as the standard deviation of the population. Remember, it was a formula. 0.09, sorry, lost to 0. Sorry about that. Hopefully that answers your question. So that came from right here. Maybe I'll even copy and paste that so we can refer to it. So the mean of the sampling distribution is the same as the population mean. On the other hand, the standard deviation of the sampling distribution is not the same. It is equal to sigma, which is 0.20, divided by the square root of the sample size, which was 30. Let's make that a little bigger because it's hard to see. And by the way, that is equal to n 0.09, comma. Now let's go 0.2 over root 30. Just throw it in Google. And you get 0.0365. It's good enough. Any questions? Oh, yeah. I would never, ever, ever assume that you know how many stocks there are in the Dow Jones. Yeah. Okay. But I like this example because it's very meaningful. And we'll see that in a minute. Okay. So now we want the probability that not X anymore, now it's X bar, is less than 0. And let's make that X and X bar. So it's the probability that X bar is less than 0. And let's find it. So now our new standard deviation is 0.0365. And really, that's the only thing that changes. Any questions on that so far? And hit calculate. And you get 0.0068 approximately. So now we're talking about less than 1% chance of losing money. Do you think you could live with that one? We decided that 33% chance was way too high. But what about that percent chance? Yeah. Okay. And not only that, so check this out. If I put money in an index fund, okay, then there's very small chance of losing money, but my expected value is still a 9% return. Whereas if you put it in the bank, your expected value is basically almost nothing, less than 1%, less than 0.5% return. So what do you think is a smarter thing to do? Put in the bank or invest in an index fund? Yeah, invest. I want to let you know, I want to be so you don't get mad at me if something goes bad, very bad. This word assume is always something you should worry about. The Dow is really not a great representative sample for a single year. Sorry, it's not independent for a single year. So you really want to do something where it really is more independent than the Dow. Do you know what you call that? And this is a business question. Do you know what you call that kind of investment if the stocks are independent of each other or mostly independent? Starts with a D. It's not a math word. Okay, if you don't know, it's called a diversified investment or yeah, there we go. Diversified portfolio. So if you have a diversified portfolio, you're better off. By the way, do you have to have 10,000? No, you could do it with 1,000. That works fine. And so it doesn't have to be 10,000. All right, so here's the thing. This is actually a much better investment than the bank. Okay, by the way, what do you think the bank does with your money?
Loans it out to
Yeah, it does two things. One, it loans it out, and the other, it does this. So if they don't have enough people to loan it to, they pop it into the market and they put it in a diversified investment and make a lot of money out of it. Just to let you know. So they loan it and they do this. So they do a combination of the two. So again, you can give bank your money or you can make money. Okay. So let me tell you a little story. I don't know if the story is, it's my personal financial strategies is I have different kinds of money. When my daughter was born, this was a very long time ago, I invested in her education. Okay. Do you think I put it in the bank? Do you think I put it in a single stock? Or do you think I put it in an index fund? Yeah, I put it in an index fund because I understand the math and I knew that especially over an 18-year period that there was basically no chance of losing money. And the returns are going to be 9% instead of less than 1%. So an index fund was the way to go. And I also, would have trouble living with myself if I lost all of her money when it was her college education fund. Okay. But I wanted to make sure that I could pay for my daughter's college education when she went to college. Okay. What do you think happened, by the way? Do you think I lost money or do you think I made money? Over those 17 years. Yeah, I made money. Okay. I did well. I did around 9%. I mean, and 9% is not total 9%. It's 9% per year. So if you talk 9% per year for 17-year investment for your child, all of a sudden there's a lot of money there for education. Okay. So then there's another kind of money, what I call play money. That's a money where I'm not okay with just 9%. I want a chance of making a bunch. Okay. Sometimes I want to make 50%. Do you think the Dow Jones, do you think an index fund is a good idea? If I want at least a reasonable chance of making a whole lot of money out of it in a year. Yeah, then that won't work. And the bank is even worse, right? So what do you think I do? I put it not stocks, but stock, single stock. And I call that my play money. So I put some money into a single stock that I think is going to do well. And sometimes I get lucky, sometimes I don't. I do lose money sometimes, and I do make some money sometimes. Any questions on that? Okay, and I will let you know that in a few weeks, I'll talk about an example of how I do it. Okay, we don't quite know enough statistics yet, but I'll talk about an example of how I made not 9%, but 200% in a year. Okay, and knowing I would, or was pretty sure I would, just let you know that, using statistics. So statistics can make you a lot of money. Just let you know that if you do it right. Okay. And
yeah, if you already have that laying around, but there are a ton of people in this country who live paycheck to paycheck who cannot afford to sacrifice anything.
so the key is live in poverty for a few years, in complete poverty, and save money. Says, in other words, spend a little less than you make. I know that's hard. Now, I'm not talking about as students. I'm talking about once you're not a student anymore. Once you graduate from college and you get a like a full-time, I'm not talking about $150,000 job, but maybe you'll make 35,000, maybe 40,000. And then you can, if you make 40,000, you can spend 35, save 5, live in poverty. And then you got the 5, and that 5 will make the rest of your life so much better. Just let you know, because then you could do this kind of investment. As students, that's a whole different thing. I mean, as a student, that's a whole, that changes everything. But once you're not a student anymore, then hopefully your life will change for the better financially. It's one of the points of going to college.
Honestly, given the cost of college, the likelihood of that kind of lower now that people have $100,000 of debt that they won't be able to pay off with any job they can get. So there is.
But I will tell you can get 9% doing this way. Whereas your percent you're going to pay for your interest on your loan for your college is less than the 9%. So it's actually worth not paying off your college loan and investing what you've got and paying the minimum. So that's how you do it. I'm not kidding. And that's how you make extra money. But you have to do it right. And you have to understand the statistics. Okay, once you're out of college. So just let you know, there are financial ways of making it work. Okay. And I was, by the way, very poor in college. Okay. So none of this stuff, I did not have my daughter while I was in college. That happened after. Just let you know that. Any questions on this example? Okay. So this is a big example of the central limit theorem. Is it's a way to understand how to reduce your chance of losing money. And what we really did, I want to focus on this little piece right here, is we reduced the standard error. Any questions on that idea? So let's do another question. I'll even throw it the same standard deviation. Okay. So suppose you want your standard error to be equal to, you don't want it to be 0.2 because that was a standard deviation, but let's say you want it to be equal to 0.1. Let's make it, how about 0.01? So let's suppose you want exactly 1%. How big a sample size do you need? So in the stock market idea, how many stocks do you need in your purely diversified investment is a kind of financial way of saying it. But it works in any cases that we do. Any questions on the question? Okay, what don't we know this time? What letter don't we know when it says how big a sample size do you need? Because it helps to understand what letter you don't know. What's the letter we use for sample size? What letter do we use? What's the letter we always use for sample size? X is the variable. So that's the outcome of the experiment. How much money you're going to end up making. That's X. What's sample size? Do you remember? I don't see y'all jumping in. Okay, the sample size, you always use the letter N for. N for number in your sample. Number of people you surveyed or number of stocks you bought. So N. So now let me remind you about the central limit theorem again. And that is sigma sub x bar equals sigma over root n. Any questions on that? So now we don't know n, we know sigma sub x bar and we know sigma. So now we can write down sigma sub x bar is 0.01. That's what we want. That's our standard error. Is equal to sigma over root n. And sigma is 0.2. And then it's over root n. Any questions on that? All right, we need n. How do we get n? Little algebra, basic algebra. So how do we find n? Not quite. Let's do the algebra. Root n is in the denominator, so we can multiply left and right by root n, and you get 0.01 times root n equals 0.2. And again, I want n by itself, so I'm going to divide by 0.01. So I get root n is equal to 0.2 and then divided by 0.01. Any questions on that? Okay, and 0.2 over 0.01 is what? 20. So then I'd square both sides and I get n equals 400. Any questions on that? So I need to have a sample size of 400 in order to make this work. Any questions at all on this particular problem, this example? Okay. Let me state, I'm not going to do much with it because we don't have that much time left, but I do want to state the next big theorem. And it's more of the central limit theorem. And that is the central limit theorem for proportions. In fact, I'm going to make it bigger because it's that important. Okay, so here's the deal. Our examples that we've had and everything we've done so far today basically were all about means. But a lot of times you do a study that's a yes/no question. And you can think about the same idea. You can talk about the sampling distribution for sample proportions of sample size n, which means let's suppose you wanted to find out, I don't know, the percentage of Americans who have been vaccinated. So you do a survey and you might ask 300 people, have you been vaccinated? And they're going to say yes or no. Okay, so what you want to do is you want to say, well, of all possible samples of size 300, what is the mean of all the samples proportions? And what is the standard deviation of all of the samples proportions? So the first thing is, let me write this out. P hat. So P hat, I don't think you've seen this symbol before. We've seen P. P is a population proportion. So let me write this out. Maybe under here. So P there we go. P is the population proportion. And P hat. So P with a hat on top is the sample proportion. Okay, believe it or not, when I first taught this, they used Greek, but the problem is, what's the Greek letter for P? And the hint is, you all know it, it's pi, and it confused the hell out of everybody because they all wanted to be 3.14, and it just didn't work. So what I noticed is all the books, everyone seemed to change to this P hat idea. That happened around 22 years ago. So we use P hat, P with a hat on top, very hard to type, but easy to say. So P hat is a sample proportion, and the big theorem is that the mean of all possible sample proportions is equal to the population proportion. That's another way of saying that the sample proportion is an unbiased estimator for the population proportion. And then sigma sub P hat, so the standard deviation of all possible sample proportions, is the square root of PQ over N. And let me write down Q is defined as 1 minus P. So if P is a proportion of yes answers, then Q is a proportion of no answers, because 1 minus the proportion of yeses is the proportion of no's. So if you take the square root of the proportion of yeses, times the proportion of no's, divide by your sample size, that's going to be the standard deviation of all possible sample proportions. Any questions on that idea? We call that the standard error for proportions. And then 30 is not the key number anymore. When you're talking proportions, you want NP, which is the predicted number of yes answers, and NQ, which is a predictive number of no answers, must be greater than 5 for the sampling distribution to be approximately normal. If they're not greater than 5, you can't use the central limit theorem. So I just wanted to end by stating the central limit theorem for proportions. And I want to let you know on Tuesday, I'll start out with talking about what we're doing for the day. And then hopefully, you take a quiz. And I won't quiz you on the central limit theorem for proportions because I didn't give you an example, but I will quiz you on the central limit theorem for means. Just let you know that. And so you can be quizzed on the central limit theorem for means. Then after that, I'll review the central limit theorem for proportions, do some examples of the central limit theorem for proportions, talk about sums, which is really quick actually, and then we'll review for the exam. Don't miss Tuesday. You don't want to miss the review for the exam because it's a really important experience to get. So I figured I'd let you know what's going on coming up. So I'm going to stop my share. And I'm going to stop the recording because it's 5:50.